Have you ever tried to capture the mesmerizing dance of a hummingbird's wings? That rapid flutter, moving so fast that to the human eye, it seems almost like a mere blur? Well, today we're diving into a world where things happen even faster than the fleeting flap of a hummingbird's wings. The Nobel Prize in Physics for 2023 takes us to this world, a realm where the nuances of nature perform an intricate dance, a dance of light and electrons, of attoseconds, allowing us to see what an electron does as a result. Imagine, for a moment, the entirety of time since the Big Bang. Well, let's assume Big Bang is a fact that is 13.8 billion years. Now imagine capturing a single second from that span. That's an attosecond. Anne Lhuillier, Pierre Agostini, and Ferenc Krauss, the trailblazers of 2023, showcased that with the right tools we can, in a manner of speaking, listen to the Electron song. And the tool they employed? Extremely short bursts of light, or attosecond pulses. Attosecond, a billionth of a second, the time it takes for an electron to jump between atomic orbitals, or for an electron to be ejected from an atom by a photon, often occur on the attosecond timescale. Femtosecond, a millionth of a billionth of a second. An atom in a molecule typically completes a single vibration in 10 to 100 femtoseconds. Even fast chemical reactions generally take hundreds of femtoseconds to complete. Nanosecond, a billionth of a second. A beam of light shining through a vacuum will travel only 30 centimeters, not quite 1 foot, in this time. Microsecond, a millionth of a second. That beam of light will now have traveled 300 meters. Lhuillier's experiments provided a deeper understanding of how laser light, when passed through gas, can interact with atoms to produce overtones. Light is composed of waves, each having its distinct wavelength that corresponds to various colors. For instance, the red light has a wavelength of around 700 nanometers and oscillates hundreds of trillions of times per second. The wave's length determines the shortest possible pulse of light, with the traditional limit being a femtosecond. The key to producing these ultra-short pulses lies in the realm of overtones. When laser light passes through a gas, it interacts with the gas's atoms, leading to the creation of overtones, waves that have multiple cycles within each cycle of the primary wave. This is akin to musical overtones that differentiate the same note played on different instruments. Around 1987, Anne Lhuillier had effectively generated and examined these overtones using infrared laser beams through noble gases. As the laser affects the gas's atoms, it excites the electrons, causing some to detach and then reattach, emitting overtone light pulses in the process. In 2001, Pierre Agostini in France produced a series of consecutive attosecond light pulses and combined them with a delayed segment of the initial laser pulse to determine how the overtones interacted. Simultaneously, Ferenc Krauss's group in Austria developed a technique to isolate a single attosecond pulse, utilizing it for detailed studies on electron behavior. With these breakthroughs, the door was opened to study electron movements with incredible detail and precision. Now, it's essential to understand that these experiments don't see electrons as tiny dots or spheres. The Heisenberg uncertainty principle asserts that we cannot simultaneously know the exact position and momentum of a quantum particle like an electron. This fundamental principle in quantum mechanics has profound implications for our understanding of the nature of particles and their behavior. The Nobel Prize-winning work doesn't contradict or circumvent the Heisenberg uncertainty principle. Instead, these incredibly short bursts of light allow scientists to measure and study electron dynamics with unprecedented precision. But it doesn't mean that we're seeing electrons as tiny spherical balls. When we say observe or study the electron dynamics, we are talking about inferring the behavior, pathways, or interactions based on the experiment's results. The language might imply a visual representation or understanding, but in quantum mechanics, observation often means interaction and measurement rather than a traditional visual observation. So, why does all of this matter? These short bursts of light can transform how we study materials, potentially leading to advancements in electronics, medicine, and even our fundamental understanding of the universe. The Nobel Prize in Physics this year isn't just a recognition of groundbreaking work, it's a celebration of human curiosity and the relentless quest to understand the very fabric of our reality. Thanks for joining us on this voyage into the captivating dance of electrons and the illumination provided by Attosecond pulses.